Hello and welcome to this video lecture series on microwave tubes. In the last video, we have discussed about constructional details and operation of magnetron, which is a cylindrical magnetron. In this video, we will try to obtain expression for Hull cutoff voltage, Hull cutoff voltage equation, and Hull cutoff magnetic field equation. Hull cutoff magnetic field equation. So both these equations we will try to obtain, and we know we have discussed enough theory of this particular magnetron. We know that we have a cathode which is at the center and different anode cavities are placed surrounding this particular cathode, and the field is adjusted in such a way that when electrons have started from cathode, they will just graze anode and come back. So this is what is expected. So the DC electric field and DC magnetic fields which are crossed together, because of the magnetic field present, what will happen, the electrons which will travel between the space cathode and anode, and if the magnetic field is greater than a critical magnetic field, electrons will never reach to the anode, rather they will be moving in between the space cathode anode, and the voltage we have to adjust in a such a way that beam supply voltage should be less than the cutoff voltage. So these are the two conditions for electrons to just move between the space anode and cathode. Okay, so this is how we are going to proceed for this video. We are going to obtain what is the cutoff magnetic field which will result into the movement of electrons between the cathode and anode, and also what should be the value of this cutoff voltage which will again result into the same phenomena. Electrons will move in between the space cathode and anode. So to obtain the expression for Hull cutoff voltage and Hull cutoff magnetic field, we will start with the equation of motion for electrons in this particular geometry, and this geometry is a cylindrical geometry. To understand the operation of cylindrical magnetron, you can go back and see our earlier video in which we have explained, if we have this cavity, we have a cathode in between. In absence of the DC magnetic field, electrons will go to the anode cavities in straight path. If we have a small magnetic field present, so electron trajectory will be little bent because of the presence of magnetic field. The force will be acting on electron, which is minus E into E, and if higher is the magnetic field, the bending would be more. So at specific magnetic field value, electrons will just graze anode and coming back to the cathode. So this is how the electron movement, different paths A, B and C. So C path is actually electron just grazing the anode and coming back, and if you increase the applied DC magnetic field more than critical field, this is happening at the critical field. If still more magnetic field is given, electrons will just move between the space cathode and anode, which I have drawn at the start of this video. So to determine the values of these voltages and geometry, the cylindrical geometry, so we will write the equation of motion for electrons. Since the geometry is cylindrical, we'll write in cylindrical coordinate system. Okay, so this equation is d square z by dt square minus r d phi by dt square is equal to E by m er minus E by m r bz d phi by dt. So this is the equation for motion of electrons in cylindrical coordinate system. This can be also written in other form: 1 by r d by dt r square d phi by dt is equal to E by m pz dr by dt. Let us call this as equation A, where the term E by m is electron charge and electron mass. So it is charge to mass ratio, and B0 is some DC magnetic field. If we assume that is in the positive z direction, that is why we are writing Bz. Okay, so in case of this cylindrical magnetron, the DC magnetic field is in the positive z direction, so that is why we are writing this B0 as Bz is assumed in positive z direction. Okay, so equation A we will rewrite. Equation A becomes d by dt. We will just rearrange this: d by dt r square d phi by dt is equal to E by m bz r dr by dt. So what we have done, we have taken this r to the right side, and now this r dr by dt will solve further using d by dx of u raised to n, which is equal to n into u raised to n minus 1 du by dx. So we can write d by dt of r square is equal to 2r, that is n is 2, so n u raised to n minus 1 2r dr by dt, and if you take half of that, so it is half d by dt r square is equal to r dr by dt. So r dr by dt is what now? This term r dr by dt we will replace by half d by dt r square. Therefore above equation, this equation we will write d by dt r square d phi by dt is equal to half E by m bz d by dt r square. So this term E by m bz is actually called as omega c, which is cyclotron angular frequency. It is called as cyclotron angular frequency, denoted by omega c. That is why we can rewrite d by dt r square d phi by dt is equal to half, this term will write as omega c d by dt r square. Okay, so we'll integrate this equation. To solve it further, let us integrate this equation. So integrating above equation. So integrating above equation, what is that? So it will become r square d phi by dt is equal to, this is constant, half omega c. So d by dt will, by doing integration, it will be converted to r square plus some integral constant. Now let us assume at r equal to a, which is the radius of cathode, where I will clearly write here a is the radius of cathode. So at r equal to a, and d phi by dt is equal to 0 if the magnetic field movement at r equal to a, if we consider it as a 0, so constant, if this d phi by dt is 0 and r is equal to a, so constant will be equal to what? It would be minus constant would be equal to minus half omega c a square. Okay, so if this constant is this quantity and r equal to a, so d phi by dt would be 0. Okay, so d phi by dt means there is no movement just at the uh, cathode cylinder, at the radius of cathode cylinder. So therefore above equation we can rewrite r square d phi by dt is equal to half omega c r square, and constant is minus half omega c a square. Let us take half omega c common. Let us take half omega c common. So it is r square minus a square. Now let us take this r square to the right side. So d phi by dt is equal to half omega c 1 minus a square by r. So kinetic energy of electron, we know that kinetic energy of electron, it is half mv square, and that is equal to static energy, which is ev. So we have the r and phi components for electron velocity in this magnetron. So for r and phi components of electron velocity, okay, so electron velocity v square is 2ev by m by solving this equation, and it has only r and, sorry, small v should be there, it has r and phi components. So vr square plus v phi square is equal to, as per this our knowledge of cylindrical coordinate system, we can write is dr by dt square plus r d phi by dt bracket square. Okay, now at r equal to a we have solved this, means at the edge of cathode, because a is the radius of cathode. So at r equal to b, at r equal to b, and where we know that where b is the radius from the center of the center of the cathode to the edge of the anode. So b is equal to the radius, you can see b is equal to the radius from the center of the cathode. So this is center of the cathode to the edge of the anode, so that is b, and earlier we have taken a as the radius of the cathode. Okay, so at r equal to b, v is equal to voltage is equal to dc voltage v0, and what is dr by dt? So dr by dt would be equal to 0 at r equal to b, because there is no movement in the direction r with respect to time for the electrons, right? So v equal to v0, so above equation we can write 2 this v square, we can write 2 e v0 by m is equal to, now this dr by dt is 0, so the only phi term would be there, 2 ev0 by m into r square d phi by dt square. So let us put r equal to b, since we are doing this for this case. R equal to b d phi by dt. What is the movement of electrons? That will be only in the phi direction. Okay, so this is 2 e v0 by m equal to this. So d phi by dt, d phi by dt, from our earlier equation we can see it is half omega c 1 minus a square by r square. So this r will be replacing with b. So d phi by dt is half omega c 1 minus a square by r square. R is b, so it is b square. And again this term b square d phi by dt square is b square d phi by dt square is equal to 2e v0 by m. Now let us rewrite above equation, which is this equation, with the d phi by dt which we have obtained. Means use this d phi by dt in this particular equation. So it becomes, to rewrite above equation with the d phi by dt, so it is b square. What is d phi by dt? It is half omega c 1 minus a square by b square, its square, is equal to 2e v0 by m. Okay, now solve it further and we can write it b square into 1 by 2 omega c b square minus a square by b square whole bracket square is equal to 2e by m v0. So under root of both the sides, taking square root on both the sides, square root on both sides, we will get b inside the bracket half omega c b square minus a square or b square is equal to under root of that. So that is, I can write raised to half. Now just rearrange it, multiply inside the bracket by this b. So it is b omega c b square minus b omega c a square divided by 2b square. This term would be same of the right hand side. Okay, now let us take b cube common. So it is b cube, b into b square, b cube into omega c, we know it is e by m b0. So we have written it where we have written e by m bz, we have called it as omega c. So e by m b0 we will be using, which is in z direction, magnetic flux density. So b cube e by m b0, we are replacing this omega c minus, again what we are taking here, will be writing this b omega c is e by m and b0 a square. Okay, is equal to 2e by m v0 raised to half and into this denominator side 2b square we have taken to the right side. So we have not taken as such common, we have just multiplied this b into b square, that would become b cube, and this 2b square we have taken to the right side. So next let us have b0 common, capital B0 DC magnetic field common. So remaining terms are like this, b cube e by m minus b e by m a square is equal to the same term 2e by m v0 raised to half 2b square. Now just rearrange inside the bracket, again take b cube e by m common, so it would be 1 minus a square by b square. So it is 2, again same term. Okay, now we can write for B0, that is what ultimately we wanted to determine for Hull cutoff magnetic field. B0 is equal to 2e by m V0 raised to half 2b square divided by b cube e by m 1 minus a square by b square. So cancel out the common terms from numerator and denominator. B square cancel with the b square, 1b will be there in the denominator. So finally we can write for B0 is equal to 2e by m V0 raised to half 2, this e by m will go to the numerator, we'll write is m by e divided by b into 1 minus a square by b square. So let us try to cancel out the common terms. 1 under root 1 root e can be cancelled with this root e. 1 root m can be cancelled with this root m because this term is under root. So the remaining b0 would be then 2 under root 2, so that can be under root 8, then under root m, which is from here, and 1 under root e because 1 has cancelled with this, so 8 m by e, and this root v0. So all this thing is raised to half under root, and in the denominator we have b into 1 minus a square by b square. So this is actually the cutoff magnetic field equation which we have obtained. So the magnetic field has to be greater than this for the electrons to travel between the space cathode and anode. So we'll write here this is Hull. Why Hull? Because Hull has invented the magnetron, so the name to this equation is given Hull cutoff magnetic equation. And if B0 is greater than Hull cutoff magnetic equation B0C, applied DC magnetic field is greater than this B0C cutoff field for a given V0, which is DC field. For a given V0, the electron will not reach the anode. The electron will not reach the anode. They will just move the space between cathode and anode. Similarly, one could determine the cutoff voltage equation, which is Hull cutoff voltage equation. So just by rearranging this, we can find the Hull cutoff voltage equation. So to find Hull cutoff voltage equation, so we'll rearrange this equation only, this one, B0 is equal to, we'll write like this, root 8 root m by e under root v0, which is the same equation, b into 1 minus a square by b square. So from here only we have written b0, so under root 8 under root m by e under root v0, b into 1 minus a square by b square. From here we'll determine what is v0. So we can write under root v0 is equal to b0 into b into 1 minus a square by b square divided by root 8 under root 8 under root m by e. Okay, so squaring on both the sides will get v0 is equal to b0 square b square 1 minus a square by b square bracket square divided by 8m by e. So that is finally v0c, that is cutoff voltage equation, hull cutoff voltage equation. It is E by 8m b0 square b square 1 minus a square by b square bracket square. So this equation is called as, this is hull cutoff voltage equation. And if applied DC voltage is less than this cutoff voltage for a given DC magnetic field, the electron will not reach the anode. And why this should be less? Because we don't want electrons to reach anode, and we know that the electron velocity can be controlled by using this voltage, which is 0.593 into 10 to the power 6 V0. If we increase this V0 beyond the specified DC voltage, electrons will straight away move towards the anode without much influence of that magnetic field. So that is why V0 has to be less, so that electrons will move the space between the anode and cathode. So that is what we have discussed about the hull cutoff magnetic field and hull cutoff voltage equation for the cylindrical magnetron. Thank you.